Yeah, sounds good. Thanks for the introduction, David. Okay, so let me see. I'm going to give a talk today on the topic of artificial intelligence and how this kind of plays in with the personalized in silico cardiology project. So I'm not planning to give a technical webinar here. I think it's a bit challenging with the different backgrounds of the audience. So what I wanted to do instead was to kind of take a step back and discuss why artificial intelligence is getting so much hype these days, where it's being used, and how we might want to link that into this project. Let's see here. So I'm going to try to keep it really basic, keep everyone's attention. So what I wanted to just go over is the kind of the who, the when, where, what, how, and why of artificial intelligence and why this is such a big thing in technology these days. So I would start with the who and who am I, why am I here, why am I talking to you. So I kind of want to give a background into my studies and where I'm coming from. So I started in 2010 a PhD at INRIA in France, and this was on the topic of computational statistics. And then in 2013, I moved to Norway for a postdoc at Simula, and that was in machine learning. And in 2017, I moved over from academia to industry and joined GE Healthcare as a data scientist. And I think what's interesting about my background is that the topic of what I've been focusing on in each of these positions, the name is different, but the core technologies, they're actually more or less the same. So maybe some new tools have developed in the meantime, but kind of what's changed between 2010 or even before when I was doing my master's in population modeling with Bayesian statistics, similar techniques. We were talking classification, regression, and that's kind of what I've been doing through each of these positions. So what's kind of interesting about that is how we've kind of just changed the names that we use for things. So back in my PhD days, the big thing was computational statistics. So machine learning wasn't really a term that was known at that time. So there was no courses on machine learning and no education about that. It wasn't really a thing back then, especially not when we were talking medical applications. But by the time I started to do my postdoc, then machine learning was everything. It was a buzzword that we use for everything. And if you want to write a grant application or you want to write a paper, then you're for sure going to drop the term machine learning in there. So the same kind of goes now. So you'll notice that I changed the title of this talk from machine learning to artificial intelligence, because that's kind of the term that we're using these days. So back in, say, 2013, the only way we were really thinking of artificial intelligence was in robots. Like you would think of Will Smith in iRobot, great movie. That's kind of what we thought of artificial intelligence, and now it's a term that we're using all the time. So it's really amazing how fast this whole field is moving forwards. It's really, even in my time, let's say, it's just incredible developments that we're seeing and that we're now a part of. And if we're talking kind of the father of artificial intelligence, then the person that comes to mind is Alan Turing, who was the first to kind of propose a way that we could analyze artificial intelligence, or a way that we could measure it. So back then, this was in the days when the term computer was used to refer to a person, because the concept of a computer that we consider now, that didn't exist back then. So he kind of proposed this way that we could test the intelligence of a machine. And back then he was proposing using natural language processing. And he kind of predicted that by the year 2000 that we would be already having technology that would be able to pass these tests. So then kind of when we talk about the when, we're thinking, okay, when did AI really start being used? Because of course the concept of artificial intelligence that goes back to the ancient philosophers' days. But if we're really talking in modern history, we're kind of thinking back to the 1940s when the first computer, the ENIAC, was developed, and then move forward to the 1950s, and that's when we had development of what's kind of the first neural net, or what we kind of can recognize with respect to the technologies that we're working with today. So that was with the proposal of the perceptron, and then we kind of moved forward. Nothing happened for a while into the 1990s when computational statistics kind of brought these methods into applications, and then we had the first computer beating a human in the game of chess. NVIDIA coined the term the graphical processing unit that we're referring to in all areas of technology these days. In the late 1990s, NVIDIA also developed the first GPU processing software. So that's what we know now as CUDA. So, okay, what's kind of been happening in the last 20 years? Well, basically the technology has been focused towards bringing these kind of tools to everyday use. So making the software easy to work and interact with, and making the GPUs kind of affordable. So now most computers that we're using, they have GPUs. So if we talk about kind of mapping performance potential across time, we kind of know that human performance is quite linear. We can't really go beyond the computing capacity that we have inside our brains. But if we talk the potential of a computer, it's probably actually even faster than this, because computing technology is advancing so rapidly, and we're getting cheaper accesses to more resources. So we're kind of at this really nice position now in technology where we're kind of reaching this point where the computers are able to perform at the level, or even in some applications outperform humans. So it's really, like, in terms of timing, we're really at a super exciting point in history, I think. If we talk about volumes of data and performance, the human brain, we kind of have a limited capacity. It's like a friend used to use the analogy that she has a cup, and as soon as the cup gets full, some stuff comes in, but that means some stuff goes out. It's kind of, I kind of like that. It's and it's a bit like that. We can't process too much. We have limited performance capabilities, but when it comes to machine learning, you know, this can grow over time. And if then we consider deep learning, then the potential is really significant. And now that there is access to many different deep learning frameworks, and the computing capacity is just growing significantly, and we're really at this crucial moment here. So if we talk about where AI is being used, it's kind of even more a question of where it's not being used. So in our cell phones, Spotify is using AI to predict our interest in music, and our emails to block spam, and our credit cards to make sure that no one's stealing the credit card, detecting fraudulent behavior, and in our cars with Google Maps, and now with Tesla. So I was in a colleague's Tesla actually a couple of weeks ago, and then it was doing this automatic speed thing. So what was the kind of the high-tech version of speed cruise control? And this colleague was showing that this Tesla also has the automatic steering. So we didn't try it out because it was kind of with the disclaimer automatic steering, and then in brackets beta version. So we kind of didn't want to give that a go on the highways. But it's kind of crazy that this technology is available now, and in healthcare, us at GE and others in industrial groups, they're all kind of jumping on this artificial intelligence bandwagon. And if we talk about kind of where artificial intelligence is being used, it's being used to improve the way that we're shopping. So with Amazon, they're using artificial intelligence to automatically predict our tastes and what we want to buy. If we talk about social media, Facebook's, of course, using artificial intelligence to automatically tag photos in cars in the Tesla, and also automatic flight routes are using artificial intelligence these days, and even in the way that we're voting. So if we talk about Cambridge Analytica and the role that AI had in the Trump election and in Brexit, it's kind of crazy and also a little bit scary about how much artificial intelligence is kind of playing a role in our everyday life now. But it's also exciting, and there's many cool things that we can do with AI. So I'm using this term a lot, and I think it's probably time to define that. So if we talk about artificial intelligence, we're talking about computers with the ability to reason as humans. And then a subset within that, we have machine learning, which is computers with the ability to learn without being explicitly programmed. So of course, this already has great potential if we want to model the computational phenomena within the heart, for example, where these are complex dynamics that are difficult to kind of assign different parameters and to find the correct models. So having the ability to learn without being explicitly programmed is kind of expanding the amount of applications that we can apply computing to. And then within the field of machine learning, we have deep learning. So this is a network capable of adapting itself to new data. So when we're talking about learning, I think it's nice to just mention what the learning process looks like for humans. So the way we kind of learn ourselves is through experience, so some concrete experience. So if we see an object and it's given a label that we call cat, let's say, then this is kind of our experience of this information. And then we reflect on this. Okay, what does this mean? This object is contained within the label cat. And then we think about this, we take the abstract conceptualization, and then we kind of apply this to new cases. Okay, we think this one's a cat, and this one's a cat, and that one's not a cat. And then we kind of learn, okay, no, we were wrong. That one's actually not a cat. That one is a cat. Okay, what is it that defines a cat? And that's kind of at a course level how we would learn as humans. And it's kind of the same with machines. So we can give them data where we say we have this object and that object has the label or class cat. The computer doesn't reflect on that. Of course, it just takes this information as a given, but then and kind of what we could consider a thinking process, what we would do is to try to give to the computer certain features that are descriptive of this item being the term cat. So maybe 2 pointy ears, 4 legs, a tail. And then we apply this to new experiences and then learn as we go from the failures. So I think when we're talking about artificial intelligence and machine learning, it's nice to think about what it means really to learn. So we have, with machine learning, we get some kind of input. We extract some features. So this is the humans finding what's relevant in the data and giving this machine to some kind of, information to some kind of algorithm. And then we say, okay, this is either a cat or not a cat. So deep learning is quite similar. We take an input, the feature extraction is contained within the algorithm, and then similarly we get an output. So it's kind of machine learning, deep learning at a very coarse level. And then if we want to consider what machine learning techniques are out there, we have unsupervised learning. So this is, for example, used to reduce the dimensionality of problems. So if we're looking at big data, genome sequences, we know that not all of the information is important. So by dimensionality reduction, it allows us to look into the data, visualize it, find meaningful parts of the data, discover new structures, and feature extraction. Then we can consider clustering algorithms to, for example, recommend taste in music and Spotify, for targeted marketing and for customer segmentation. So what unsupervised learning is doing is kind of taking some data. We just have the input data, no input information from a user. So no training data, labeling is required, and then we take this, we train a model just to find for itself what are the different structures within the data, and then some processing to give out the red ones that are rounded. They're all in the same class that we could call an apple, and then the moon-shaped ones that are yellow, they're banana, so on. So this is the standard setup of unsupervised learning. Then we have the supervised learning groups, so classification, trying to detect fraudulent behavior, to do image classification, for example, diagnostics. We have regression, so looking at predicting what's popular in advertising, forecasting the weather, forecasting the market, expected life over time, and so on. So similarly, we have some input data, but now this data is labeled. So we know that these are all apples, and a supervisor is kind of taking that input and saying apple, 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 apple. Then we run it through same processing, some training, and then we input new data and we get the output. Yay, it is an apple. So then we kind of have in between the unsupervised and the supervised learning, we have in between what's called semi-supervised. So we might know that this is an apple and we might know that this is a banana. We want to try to define a classifier that divides these two groups in terms of their data. And so we don't have access to a lot more training data, or we don't have time to label the data, or for whatever reason. So we want to improve the classifier beyond this small training set, but we don't want to spend the time to label more data. But we have access to more data, so if we start to include in a classifier other observations, we don't know what they are, they're just blobs. But if we kind of map them into the same feature space that we define these two different classes, then we start to see some kind of representation of the data in terms of how it clusters, so that we may therefore infer based on this that these circles, they are probably going to fit into the green and circle shaped class, and these are probably going to fit into this class. So then we can kind of infer and test if these new observations currently unlabeled, then they fit into these classes that we have already. So then the last type of machine learning technique that we'll cover is on reinforcement learning. So used to, for example, in gaming these days, in skill acquisition, to learn tasks, and for robotics, so very popular in robotics. And the most motivating reason to use reinforcement learning is that if we consider supervised learning or even unsupervised learning, the challenge is that we can only reach the same level of accuracy as the humans, because the machine only gets the information that the human has. So it's kind of like if we're trying to learn how to drive a car and we only have the rear vision mirror to gauge the direction, we don't have any other information. It's kind of trying to learn from the past, from what others have seen before. So if we went to put that car in a new situation, in a new location, then we don't know how well the car would drive in that situation. So reinforcement learning has been used, for example, in gaming. So we can either teach the sequence of moves that are used in chess or Go, or we can teach the machine using some kinds of reinforcement learning strategies, how they would kind of follow the moves themselves based on higher score or lower score. So kind of trying to teach the machine to learn in the same way that a human does. Human doesn't learn by getting a whole bunch of pictures of cats and saying these are all cats. When you see one that looks like this, assume it's a cat. That's not how we learn as humans. So reinforcement learning is kind of, it's more mimicking the way that we learn as humans. So the way that it works, we have some data. We don't know whether that data is apples or bananas. It's unlabeled data. And the data comes in, and we have some kind of reward feedback. So this could be one step towards a final classification, and then we know that we have the sequence of events that lead to a classification, and we can train this environment with an agent, train the actions that lead to this positive result of correct classification. So then when there is a new input, the trained model is used to infer what's the label of this new data, and then based on the training that's occurred within this environment, we have the output of an apple. So this is kind of a hot topic these days in artificial intelligence, and a big area of development. So in 2015 was the first computer algorithm that was able to beat the world champion in Go, and the developers of that algorithm, their company was bought out by Google for a very handsome sum, because these kinds of methods, they have the potential to do really great things. When we can outperform a human on simple tasks, then we have the potential to really develop great things. So how does AI really work in practice? So we get some data. That data is pre-processed in some ways. The model is trained on the pre-processed data. Then on some new data, we test the model, and based on the results, we improve. We maybe get more data, change the way we pre-process the data, change the model. So kind of at the core, we have something coming in, we have some algorithm, and then we have some output. So input, algorithm, output. And if we have garbage coming in, if the data is poor quality, then it's clear that the output will be poor. So it's important to make sure that the data used in training is good data if we want to get good results. But similarly, if the algorithms are garbage, then we'll also get garbage. So it's kind of a garbage in, garbage out situation. If we want good results, then we have to have good data and good models. So if we're talking about getting the data, what we want to do is represent the population that we're planning to apply the data. So getting a diverse range of data. So if we're talking healthcare, getting data from different geographical sites, from different clinical sites, and making sure that we have an even balance between the different groups. So this in itself is a big area, and something that's been referred to now as data being the new oil, because data is such a valuable commodity these days that it's becoming even more valuable than oil. But if we're really making this comparison, data is not the new oil. Processed data is the new processed oil. So the value that you really get from the data is from the processing, just like crude oil is in its unprocessed form is not valuable. What's really valuable is the data the oil that you get in your tank. So the data needs to be pre-processed, so from some raw form to be cleaned and then engineered so that we get what's interesting out of the data. And so that's these two aspects are what we consider data pre-processing. So the chain is kind of like, if we're talking about deep learning, then the data is the input itself. And the way we would clean the data, merge relevant data sets, fill in the gaps, so whatever is missing, standardize the data so that it looks the same despite where it comes from, kind of thing, normalize the data so that it's within similar ranges, remove any duplicated data, otherwise the data that we do have might be overrepresented in the population. Verify and enrich the data, and then export and go back to the start. So this is kind of an ongoing process, and coming from an industrial perspective, this is kind of the core amount of work that's involved with an AI application, is really getting data and making the data useful for artificial intelligence algorithms. So then in addition, we can enrich the data by performing augmentations or rotations or translations, blurring, change the size, the color, basically anything we can do to make more data out of what we already have. If we're talking about machine learning, then the data is both the input data itself and also the features. And the way we can enrich the features is by casting the features into a different space. So for example, we have this kind of data in 2D where we can see there's a difference. There's this pink squares and the circles, which they clearly are divided, but if we try to put a linear classifier through that, there's no way that we can meaningfully divide this data. But if we project the data into a higher order space, so for example, one kind of represented here in 3D, in this space we could split the two sets. So this is kind of what we call a kernel function. So this is one way to make the features more meaningful. So, and these kind of actions, that requires quite a deep knowledge of the data that we're working on. So I kind of really like this skit because I think it really it covers so many things. Like if we're talking about machine learning or artificial intelligence, everyone thinks that we're working with robots, we're going to take over the world, or working in these huge data centers, or doing some crazy mathematics, really cool higher dimensional feature analysis. And really what it boils down to is writing a bunch of different learning algorithms against our data. So the way that we kind of use models, there's no meaningful mathematical formulation to say which is the best model. So the key is kind of to pose the question. So if we have a question like, is this A or B, so a classification style, then we would use potentially classification algorithms. If we're wondering who's the weirdo in the room, we could use anomaly detection. If we want to know how many we should expect, then we would consider regression, or how things are organized within a population. Then we would use clustering. But of course, different algorithms can be used if we pose a question in a different way. But the way we kind of start is by thinking about what's the question I have, and then I can consider the different techniques I use to answer that question. So then the way we would test out the models is we take kind of some actual data that we have. So we have a bunch of cats and a bunch of pigs, and then we compare it to some predicted labels that we have on some new data that we didn't use to train our algorithm. We would kind of count out how many of the cats were truly labeled as cats, and how many cats were falsely labeled as pigs, or how many pigs were falsely labeled as cats, and how many pigs were pigs. So then we look at, okay, how can we compute a way that we evaluate what's the accuracy of our model? And then the way we could do this, or one common way to do it, is to take all the cats and all of the pigs that were correctly classified and compare that number to the total number of right pigs, right cats, and wrong pigs, wrong cats. And then if we want to kind of develop or improve our models, we kind of use this information. We're kind of here now based on this metric that we're using to evaluate the performance, and we want to go be better in the future. And so we need to improve the algorithms, so the tuning of the parameters within our algorithms. We may want to look at the features that we're using in the models. We may want to look at which features were actually useful, and we could consider combining different algorithms. And kind of the biggest thing that we're going to do is to get more data to learn from. And if we want to go better, we basically are going to do a bunch of these things in combination until we reach the goal that we have, or our expected level of accuracy. So then I said that I would kind of bring this back into the scope of personalized in silico cardiology and why we would use that. So first of all, big motivator in clinical settings is to save time, of course. We want to save time, which also, as a direct effect, saves money. We also want to improve accuracy so that diagnosis and therapy planning are better. Good health is the #1 priority in everyone's life, so we want to make sure that the medical technologies that are used to diagnose and treat patients is as accurate as it can be. And so if we're talking about time, then I'll come back to this slide I showed earlier about how computers can significantly outperform humans. So only slightly right now, but we know that moving forward, the potential is so high. If we consider types of applications where we can save money, one is robot-assisted surgery. Another is nursing assistance, so providing feedback for patients without having to physically send a nurse. To improve administrative workflow, and this is a big one. Similarly with fraud detection, we don't want to compromise patient confidentiality. For correct dosage, so in pharmacology, to have personalized drug dosage so that you're not taking more drugs than you need to, both for financial reasons, but also you don't want to be putting extra medicine in your body when you don't need to. Also to connect machines so that we have a consistent setup in the hospitals for clinical trials, for early diagnosis, and that's key, of course, in saving money, is if you can get the diagnosis nice and early, then you can treat it before it becomes something serious. Obviously, something that's very interesting for us at GE is automated image diagnosis, so taking the information that's available and extracting the diagnosis or the pathologies that are visible within those images, and of course for cybersecurity. And if we put numbers on these, it's really a billion-dollar industry. So this is the potential for saving just by having AI methods for these it's huge. And if we consider one use case, if we're talking about kind of improving accuracy, one big cause of concern in terms of cardiology is sudden cardiac death. And this is kind of scary because many athletes are dying without prior problems. So professional athletes suddenly dying from sudden cardiac arrest. And it's an area where there's very little known about why some patients suddenly go under cardiac arrest. So what is this exactly? I'll just show a quick video. So All right. If we're talking about risk assessment in sudden cardiac death, the main way that this is evaluated now is through the measurement of ejection fraction, which is the amount of blood pumped out of the ventricle divided by the amount of blood in the chamber. So this is kind of one very coarse measurement that's used for many different diagnoses in cardiology. And the problem with this is that when it comes to sudden cardiac death, patients that are identified as having ejection fraction less than 35%, this is for sure this patient is going to get an implanted device. And so that's good. So then we know, okay, we need to be careful. These patients are at risk. But the problem is that for every patient that receives life-saving shock from an implanted device, 17 others have to have the same device implanted. And this is both invasive and also expensive. So it's kind of a very crude way to risk stratify patients for sudden cardiac death. So the reason why this is so challenging is because the heart is such a complex organ, so it's very difficult to isolate what's the problem. We have an organ that's beating on average 80 beats per minute, so this is very significantly slowed down video, but 80 beats per minute in a lifetime, so that calculates to more than 3 billion beats. And if we're to look at the structure itself, have very complex structure. I found out as well in the presentation yesterday. And if you look even just at valves here, these valves, then it's a piece of paper. So it's kind of crazy that they managed to maintain the function 3 billion times in a lifetime. So when something goes wrong, we can kind of think, is it structural? Is it something to do with ventricles, the atria, the valves, complex fiber network? There's, of course, this is an electrical organ as well. So is there something wrong with the electrical propagation through the fiber network? Is it something related to the motion of the heart? Because we have a dynamic organ to investigate. Is the hemodynamics? Is there some mechanical problems with the heart? So trying to model this, like in the personalized in silico cardiology program, if we try to look at any one of these factors in isolation, it's not bringing the full picture of this complex organ. But each model in itself is kind of, that's, as you know, that's one research project in itself. You know, we have Joao working on the blood flow, and we have Maciej working on the structure, and these alone, looking at these in isolation, it can bring some information, but it's kind of missing the full picture there. But the way that we can kind of bring all of this together, all of these multi-physics, is through artificial intelligence. So it's not only just that this is a multi-physics organ that we're trying to model, it's also an organ that varies significantly even at a spatial level. So changes at the protein level can affect the cell membrane up to the cell level, tissue, organ, and even on the whole body kind of scale. And not only that, we have multi-scale organ at temporal level. So we're starting from the millisecond level of the action potential. So slight changes in the action potential will over time affect the cardiac cycle, short-term remodeling as well as long-term remodeling. So if we're trying to do in silico modeling of these things, we're dealing with such a range of spatial scales and such a range of temporal scales and so many different physics. Bringing this all together in one model, it's not really possible right now. But we can do this by machine learning or artificial intelligence. So, for example, what we could do with this population is, if we know that these patients will get life-saving shock, so they would have, in other cases, died if they didn't have the device, what we can do is we can take a look at these patients and see what are the commonalities between them. If we're talking their hemodynamics, what is common between them in terms of those parameters, what's common in terms of structural parameters, and we can kind of bring this together and build a full picture of this population and use that to predict in a new patient what's their risk and kind of provide information for the clinicians about how they should risk stratify their patients. So I wanted to try to segue a bit between the talk yesterday from Sarnana and just give a kind of a glimpse of what we're doing ourselves at GE to bring artificial intelligence into improving diagnosis in our system. So this is showing scanning, and when we store, the system is automatically detected what's the view that we're seeing on screen. So just by taking this image information from other images that we've given to the system to learn from, it's learned, okay, that's a 4-chamber image. We saw that yesterday with Farnana's talk. This one's a 2-chamber. And of course, we don't show this label for the user. It's kind of Captain Obvious to tell them what's the view that they're scanning on screen. But what's interesting is to take this information. Here we're automating the workflow for them. We're finding what's the images that they should run analysis on. And we can do lots of cool stuff in the background, even just starting from something as simple as detecting what's the view on screen. So we're kind of, that's what we're working towards. And there's, of course, many cool things to do in the future. And kind of, if we're talking about the cool things to do in the future, then what's worth mentioning is kind of what's the bottlenecks that is preventing the development these days. So the main thing that's an issue now is, according to PricewaterhouseCoopers, that did a study on patients and what they feel towards allowing artificial intelligence to provide them with some medical information. 55% were positive towards this, whereas 38% were not. And so that's kind of, if only half of people are really feeling confident about the results from artificial intelligence, then we still have some way to go to convince them. And of course, there's this classic problem with radiologists worrying that their jobs are going to get stolen because suddenly it's much easier to do image analysis with artificial intelligence. But this is really, I think this is probably an argument that even the radiologists and the communities are kind of getting their head around the fact that it's not stealing their jobs, it's taking away all the boring aspects so that they're free to do the more interesting stuff that's kind of requires the human eye. And then on the flip side, we have a big regulatory challenge to try and face. So, of course, when we're talking artificial intelligence, there's the question of data privacy, and this is especially relevant now with the new data protection laws coming into effect in the EU from last year, and then coming in the US next year. So there's, of course, this way of how do we use all this information, important information from patients when we can't really deal with the data. You know, there's a lot of factors to weigh in there. And of course, from a regulatory aspect, you know, if we don't have a doctor making the diagnosis, then who do we blame when something goes wrong? So it's kind of, from a legal perspective, this is an ongoing challenge to consider. If a computer makes a diagnosis, is the manufacturer of that medical device to blame? Is it the hospital? It's still a kind of uncertainty there. I think this is something that at least the FDA are trying to be forward-thinking and trying to acknowledge that we cannot hinder progress in these areas because, of course, the number of accidents or misdiagnoses, when we can automate things, these are significantly lower than when these are done by humans. So it's something that it's getting better with time, but it's especially slow when we're talking healthcare, and that's why healthcare is so far behind in the development of artificial intelligence compared to like gaming or streaming or the other big technologies. So I kind of want to just wrap up there with a few conclusions, and I hope based on this webinar I've kind of made it clear that AI is super cool, can be used for a lot of cool stuff. If it's used well, it can really improve healthcare, and that's exciting, and it's exciting to be a part of that. But at the same time, we need to kind of tread carefully. We don't want self-driving car kills a person situation where we suddenly lose the trust of people that don't understand the technology. We want to do this well, and we want to change mindsets so that people are open to new technologies moving forward. The final thing I kind of wanted to say was that there's so much content online if you want to get your hands dirty and try these things out yourself. And like I showed in the skit earlier, the key thing if we're talking machine learning is